were discussing about the interferences in the flame atomic absorption, and we were discussing about the elements like refractory oxides like this molybdenum, vanadium, titanium, etc. And this slide I had shown you in the last class, that is number 184 slide. And this we have maintained that it has been observed that for elements like molybdenum, vanadium, titanium, aluminum, barium, yttrium, dysprosium and holmium, there is an enhancement in the absorbance values, while there is no enhancement in the case of less refractory elements like Cu, cadmium, cobalt, nickel, etc. The other type of compound formation is the alkaline earths forming refractory phosphates and double oxides in the flame. For example, we have discussed that strontium reacts with aluminum or silicon to form refractory oxides of strontium aluminum, that is SRO Al2O3, and also it can form SRO SiO2. These are double compounds. Similarly, with phosphate it forms calcium phosphate during evaporation of the liquid droplets in the flame, and this compound is converted to calcium pyrophosphate in the flame with heat, and it is very stable in the air acetylene flame. So, what we are essentially discussing is, if there is a possibility for the formation of the oxides, refractory oxides, there is enhancement when we increase the temperature and CO ratio. But in the case of elements like copper, cadmium, cobalt and nickel, etc., because the elements do not form do not form the refractory oxides, there is already enough carbon oxygen ratio to provide complete atomization of the sample. So, there is no further enhancement in the signal when we increase the flame temperature. How do we increase the flame temperature? Is by increasing the ratio of the oxidant as well as the fuel gas. So, when we are talking of calcium now, we have said that calcium phosphate forms during the evaporation and pyrophosphate during the when it is in the flame. So, this reaction reduces the free calcium atom population also, because any compound formation reduces the atomic population, and this happens in the flame as compared to that obtained from solutions in the absence of phosphate. So, if you want to analyze calcium in agricultural waters, you would normally have phosphates, and this type of interference can be eliminated by the addition of a releasing agent. What do we mean by releasing agent? Is we add another chemical which will preferentially form a complex with phosphate rather than with calcium. So, when both calcium and the releasing agent are added in a solution containing phosphate, it will react with phosphate, releasing the calcium atoms for atomic absorption. So, this concept of releasing agent is a very important concept in atomic absorption spectrometry. So, the releasing agent, we usually use lanthanum, and it preferentially combines with the interfering ion, thus releasing the analyte atom. In other cases, what happens is the releasing agents, we can add complexing agents like EDTA. So, EDTA will combine preferentially with several other elements to form compounds and then dissociate in the flame, releasing the analyte element. So, this phenomenon of formation of a complex can also be used to release the atoms in the flame after complexation. So, the addition of lanthanum releases the calcium atom. Are there any other elements, any other salts which we can add as a releasing agent? If the choice is there, you can add strontium also. So, strontium also releases calcium ions from the calcium phosphate, preferentially forming lanthanum or strontium phosphates. The addition of EDTA preferentially forms calcium EDTA complex. This is more volatile and therefore, it can dissociate relatively easily than calcium phosphate. So, now we have two choices. One is you add a releasing agent like calcium and calcium, lithium and strontium, or you add a complexing agent forming calcium EDTA complex, and then calcium phosphate will remain in the solution, and EDTA complex reaches the flame and then atomizes more easily. So, we can eliminate the interference of phosphate. So, we have published a research paper on the determination of indium in geological samples by adding a mixture of citrate. So, potassium citrate and ascorbic acid also we have added in presence of in place of lanthanum. So, this approach also works but this approach is more useful because the tripotassium citrate forms more complexes with other elements also. So, we can eliminate the interference from several other elements, and it is possible to determine indium in presence of potassium citrate and ascorbic acid. So, another way of looking at the interference is we can go by the method of standard addition. Now, standard addition technique is a very simple technique. It can be used in any analytical technique for that matter, not just atomic absorption. It can be used for spectrophotometry, it can be used in electroanalytical methods and several other methods. And what we generally do is we add a known amount of the standard, increase the absorbance to all the sample solutions also. So, the multiplicative interferences can be taken care of in the method of standard addition. So, I will be dealing with standard addition technique when I will be teaching you with polarography, not now, because even though the principle remains the same, we will have other aspects, theoretical aspects we will be dealing with, that I will be doing in the when I am teaching polarography, but it does not mean that standard addition technique cannot be used in other spectrophotometric techniques also. So, for the time being I will only say that you prepare the standards, you first prepare a standard curve of response versus concentration. And then you will get some sort of a straight line. And now what we do is we add a known quantity of the standard solution to the samples also. So, we take the sample, add the same quantity of the known absorbance, known standard, then you will get a higher response somewhere like this. And then it may, depending upon the matrix, you may get a response like this. Then what you do is draw a standard curve like this, and the difference where it cuts the x axis, this is x axis and this is y axis. So, the difference is what corresponds to the unknown. So, this is in principle the standard method, standard addition technique, We will study more about it later. Let us understand that this technique can be used to eliminate the interferences, but to what we can eliminate is we can eliminate the multiplicative interferences can be taken care of and not the additive interferences. What we mean by this is, if the sample is more complicated in terms of presence of other concomitants, then we can take care of the interference by doing the standard addition technique and not the additive interference. Additive interferences means you add some reagent like a releasing agent or a complexing agent, etc. If that substance interferes, then you cannot take care of that. But if the sample itself is complicated like seawater, a plasma or urine or some other substance with high salt content, etc., then it is possible for us to determine the unknown using the standard addition technique. So, this type of chemical interferences always takes place in the condensed phase, that we should remember. That means, we do not have much choice over the interference control because of the complexity of the sample itself. Now, let us look at ionization interference. So, in this slide I am giving a small introduction in the slide. This is also a type of chemical interference. Ionization interference is also a type of chemical interference. While the chemical interferences take place in the condensed phase, the ionization interferences take place in the vapor phase. This is the important difference. One is it takes place in the condensed phase, whereas ionization interference takes place in the vapor phase. So, when the analyte atoms get dissociated and vaporized, these interferences are observed. That is what it means in the interference in the vapor phases. The atoms of the elements possessing very low ionization potentials like calcium, sodium, potassium salts, etc., they become ionized at the flame temperature itself. This we have flame temperature itself. This we have seen while we are discussing about the atomization of the alkali salts and alkaline earth salts and other salts. We have I have shown you a table where the sodium salts, concentration of sodium atoms becomes much more in the at the flame temperature itself. So, at the very like lithium chloride, lithium nitrate, potassium chloride, potassium sulphate, potassium nitrate, many of these alkali salts have very low ionization potential. So, at the flame temperature itself, the concentration of the atoms goes up. So, again while we will revert back to the slide. So, what happens is in this slide I have shown you that instead of having more number of ground state atoms for atomic absorption, the ions of the analyte atoms will be more. That means, potassium, sodium, etc., atoms will be more. This again depresses the sensitivity, because it causes lot of interferences in the final analytical measurements. So, alkali metals are more prone for this type of interferences, like what I have told you, like lithium, sodium, potassium, rubidium, cesium, etc. So, ionization interferences are caused by mostly by alkali and alkaline earth metal salts. You would know that many of the alkali and alkaline earth salts come from seawater and other sources. The analyte undergoes the following reaction, that is M represents a metal ion, it goes to M plus and E minus, metal ion plus electron. This interference can be controlled by the addition of excess of an element whose ionization potential is low to both samples and standards. This is a very important concept, that is, you have to add the same interferent to the sample as well as standard. So, what we do is we take potassium chloride preferably due to its high purity, which is available in very high purity and lack of visible emissions in the flame. This will reduce the molecular band absorption. So, the ionization potential of lanthanum is also very close to lithium, and therefore, lanthanum, in addition to being a releasing agent, also acts as ionization buffer for metals such as calcium, magnesium, silicon, aluminum, etc. So, we can use lanthanum also alternately, because it, in addition to being a releasing agent, it also acts as ionization buffer. So, the addition of lanthanum or calcium as ionization buffer, potassium as ionization buffer, also it provides more electrons in the flame and shifts the ionization equilibria to the left. I have shown you a figure like this. If this reaction is for some other metal, I add potassium, you can put a figure, you can put the reaction equilibrium can be shifted to the metal atoms to the left, this side. So, this is the use of addition of lanthanum as well as potassium, etc., because they act as ionization buffer. So, in other words, by providing more number of electrons, the ionization is suppressed and free ground state metal atoms are restored. So, other ways of dealing with the interferences in atomic absorption are by analyte occlusion. That is, sometimes the analyte atom gets held up in the matrix and does not release in the flame. So, if it is not released in the flame, you will definitely not get the atoms in the flame, and subsequently the signal will be lower than when the atom is not occluded. So, how does it happen? It is not related to the stable compound formation or ionization, and there is no chemical reaction during occlusion between the analyte and the interferent, that means the matrix. The occlusion phenomena may be considered as chemical interference, but it is not exactly chemical interference, it is actually physical interference, but because of the nature of the complex sample what you are handling, it does not reach the flame and form the atoms. So, when the solid particles remain in the flame after evaporation of the solvent, still it consists of the atoms, analyte atoms dispersed in the matrix of the solid in the flame. So, the volatility of the matrix itself has an important bearing on the yield of free analyte atoms. So, depression or enhancement can happen depending upon whether the matrix is less volatile or more volatile than that resulting from the desolvation of the reference solution. It is a very simple concept that the sample, if it gets held in the matrix, does not release, then the occlusion we refer it to as occlusion interference. It can be considered chemical interference because the metal atoms do not form but because of the presence of other elements, the metal atoms can form if the occluded sample matrix, if it blows up in the flame, it may release the atoms also. So, it is a question of relative volatility. So, in this slide I have tried to put my thoughts about the analyte occlusion, and depression or enhancement may be obtained depending upon whether the matrix is less volatile or more volatile than that resulting from the dissolution of the reference solution, desolvation not dissolution. An example, now I want to give you an example. It is the when you are determining chromium and molybdenum absorption in presence of high iron concentration. That means, suppose you are analyzing a stainless steel, they would contain chromium or molybdenum, but iron concentration would be very high. So, determination of chromium or molybdenum in presence of high iron concentration is the example. You generally we do it by air acetylene flame. So, several observations indicate that there is no specific compound formation between chromium and or molybdenum and iron. Chromium and iron complex formation does not take place, molybdenum iron complexation does not take place, but you do get a signal which is less than chromium for chromium. So, the decrease in the analyte signals levels off only at high iron concentrations. When the concentration of iron is more, the decrease it gets, you get a lower signal and then it slowly tapers off. And the iron analytical signals are not affected, because if you want to determine iron in the same sample, they are not affected by high chromium, but if you want to determine chromium in the same sample, we have the problem of lower signal. So, this slide to give you an example of this type of interference or chemical occlusion, chromium and molybdenum absorption in presence of high concentration. So, this it is thought that at high iron chromium ratios, the chromium atoms are occluded in the iron matrix. What is the boiling point of iron? Is around 3000 degrees for this type of alloy, which is incompletely volatilized, because the temperature of the flame is around 2400 to 2500 degrees. Definitely, if the boiling point is 3000 degrees centigrade, then it will not be volatilized. In the reverse situation, now reverse situation means when we want to determine iron, iron is determined in presence of excess of chromium, that is when chromium is there, the formation of the more volatile chromium matrix does not alter the number of free iron atoms available for atomic absorption. So, this type of interference can be overcome by using nitrous oxide acetylene flame, which will give you a very high temperature, so that everything is volatilized. Alternately, you can add the addition of ammonia, ammonium chloride, sodium sulphate or boric acid or and sulfosalicylic acid to form the complexes. This way also you can handle this kind of interference. Now, I want to give you a bibliography of interference studies. In general, it is only a guideline that if you want to determine aluminum, the typical flames are air acetylene, nitrous oxide acetylene also can be used. The interfering chemical species I have listed out here: calcium, copper, magnesium, sodium, etc. And there is not much you can do the action, and if I put 0, that means if you see 0 in the action, that means there is no interference. Positive plus means positive, there is interference, and negative means negative interference. Positive interference means there is enhancement of the signal, and negative means there is decrease in the signal. So, you can see that calcium, magnesium, manganese, etc. So, some of them are I have listed only for your guidance. So, it is self explanatory, I do not have to say more regarding this. because the interference also depends upon the number of matrix size and then matrix type, etc. This serves only as a general guideline. For example, if you are determining silicon with nitrous oxide acetylene flame, you can see some sort of enhancement of the signal due to aluminum, calcium and iron. So, if you are determining silicon in air, then obviously there will be iron and aluminum in the samples, and you may get a signal like this. One has to be slightly careful when you want to determine the elements, but more details can be had from the regular textbooks regarding the interference. So, other way is another type of interference is spectral interference. This we have discussed earlier number of times. I will while discussing the interferences, I would like to include this spectral interferences. It is basically atomic absorption spectrometry is remarkably free from spectral overlaps. As you all know that the atomic absorption is based on the very narrow resonance line absorption. The hollow cathode lamp emits the emission radiation of a specific element, therefore, it is supposed to be specific for the element, and this arrangement where it absorbs the atoms of the same element, it is called lock and key effect. Hence, unlike emission technique, spectral interferences are very less in atomic absorption spectrometry. I have given you earlier couple of examples also where spectral interferences do occur. So, when an absorbing element wavelength of an element is present in the sample, but not being determined falls in the same bandwidth, we have the spectral interference. So, if there is spectral interference, difference the absorbance value will be higher than the known standards. So, there is whenever you want to determine any element using a atomic absorption, the manufacturer will provide you a book which will give you all the specific conditions for the analysis of a particular element. For example, if you want to determine copper, he will say copper you can determine the information you will get is what is the linearity range, what gas you should use, what should be the oxidant, what should be the reductant, that is a oxidant, and what should be the fuel. It could be either acetylene, air, or nitrous oxide and acetylene, like that. And then he will also tell you what is the medium in which the sample should be dissolved, and he will tell you that for a known typical concentration of let us say 5 ppm, the 1 pp absorbance should be about 0.3. Now, suppose you get higher absorbance 0.4, then you know that there could be some spectral interference, because other than the spectral interference, the analysis will not be complete if you show higher absorbance. It means either you have done a mistake while you are preparing your standard solutions, or there is an element of uncertainty in your analysis, and or there could be spectral interference. So, only 3 possibilities. One is element of uncertainty, an element of error, or spectral interference. So, because at the wavelength of measurement, it is only the resonance line. So, the in AAS, spectral interferences may be classified into 3 groups. More than one absorption line in the spectral band pass, it can happen. Non-absorbed line emitted by an excitation source, for example, flame, this we have discussed earlier, and spectral overlap in the atom source. So, atomic interference is observed in the flame AAS and reported in the literature. The non-specific absorption, we have seen that scattering phenomena, etc. You can see in the slide also this non-specific interference enhance the actual readings obtained, but the sensitivity does not improve. In this case, a spurious absorbance is added to the true value. So, it is seen either by scattering absorption line by the solid particles or absorption of the resonance line by undissociated molecules, that is molecular absorption. The scattering phenomenon is analogous to turbidity in spectrophotometry. They are formed by the inability of the flame to decompose the dissolved solids, decompose the solids, or it may be due to the formation of carbon particles in the flame. So, the magnitude of this turbidity or solid particle scattering varies considerably with the wavelength at which measurements are being made. So, scattering could be one of the important spectral interference. Normally, light scattering effects, particularly those elements that absorb at lower wavelengths. So, UV, there could be lot of interference, and molecular absorption occurs when the molecular species in the atomizer has an absorption profile that is measured at the resonance wavelength, and this problem is more serious in the wavelength region below 300. That is why we have a problem of analysis of elements like selenium and then arsenic, tellurium, etc., because their resonance lines are below 300 nanometers. So, molecular absorption bands are relatively broad compared to atomic absorption profiles. So, this is both these are known as non-specific or background absorption. So, it can be detected if the Beer-Lambert's law does not pass through the origin. That means, there could be non-specific absorption, and basically it was attributed to light scattering by salt particles, but strong evidence has been produced to indicate that scattering is often insignificant by comparison with molecular absorption, both in flame and non-flame situation, that is electrothermal atomic absorption. Thus, background absorption plays a vital role in the determination of trace elements in varied complex matrices. Therefore, different methods have been worked out by the manufacturers to control the background absorption, because spectral absorption nothing can be done. We have to go for different types of Zeeman effect, background correction, etc. But the important background corrections are high temperature flame, selection of a non-absorbing line, we can go, deuterium lamp, Zeeman effect, Smith-Hifj, all these things we have discussed earlier. So, background absorption, it can be controlled to some extent, but not fully by using high temperature flame, but which breaks down the molecular species itself can be destroyed. Then molecular absorption does not take place. So, it can be controlled by selecting non-absorbing line about 10 nanometer away from the resonance line. So, you can measure the absorbance 10 nanometers away, whatever is the absorbance, subtract it from the known atomic absorption line at the resonance line. Because it is fairly broad, there will not be much error in the background correction. So, the signal from the non-absorbing line should be deducted from the signal obtained from the absorbing line. This is a good way of treating the analysis data, that is absorption of background correction. So, the selection of the non-absorbing line should be such that it should not be absorbed by the sample matrix. That is the only criteria that is very important in choosing this kind of background correction. but it is not very scientific. So, the most widely used system is deuterium lamp. So, we have already pointed out that the atomic absorption lines are very narrow, of the order of 10 to 50 nanometers. When an atomic line from hollow cathode lamp passes through an atomizer, it will be absorbed by the atoms. So, by subtracting you can pass through the radiation through the sample and once without the sample, that is what a deuterium lamp. So, then you can modulate it and it gives you a broad spectrum deuterium lamp. So, you can correct the measure the absorbance at the using the deuterium lamp up to 300 nanometers without any problem, subtract that absorbance data from the atomic absorption signal. So, the technique of atomic absorption correction works like this. The absorbance of the sample occurring with the hollow cathode lamp is the sum of atomic absorption and background correction. This is very easy to understand for us. So, we can write AC is equal to A plus AB, where A is atomic absorption and AB is the background absorption. So, absorbance with the deuterium lamp gives you only AD deuterium lamp, but that should be equivalent to AB. Initially, both the signals from the hollow cathode lamp and deuterium lamp are made equal. This also we have understood that the background correction should be first made equal when there is no absorbance. So, the true absorbance would be basically absorbance minus that from the deuterium lamp. If you put it in terms of the ratio of absorbances definitions, you will get log of ICO divided by ICT minus log of IDO by IDT. I am just expanding these terms AC as well as AD, and this you can reorganize which represents. So, the a log of ICO, IDT and then by ICT and IDO. Initially ICO is equal to IDO, that is original signals must be made equal. Therefore, true absorbance would be nothing but log of IDT by ICT, that means intensity of the transmitted light from the deuterium lamp divided by the intensity of the transmitted light from the hollow cathode lamp. That is what we are aiming to measure. So, in this method the speed of background correction is very critical. There must be minimum delay between the total absorbance and the background correction. You understand this concept? The concept is the moment you make the measurement atomic absorption, it must be next second, next moment background should be measured. Again you can go for atomic absorption, again make the background correction after another time delay. So, the time delay between the sample and the background is very important. So, it should be as small as possible to get as true a response as possible. So, the magnitude of the background signal can change rapidly with time. For example, within 20 milliseconds the background value can change up to 0.2 absorbance. This is very high, because in atomic absorption we are talking about only about 0.3, 0.4, 0.5 absorbance maximum. So, if the background itself can change within a few milliseconds by 0.2 absorbance, the error could be quite large. So, if the difference between the measurements is about 10 milliseconds, it can lead to an error of about 0.1 absorbance. In ultra pulse system, what happens is the time gap is only 1 millisecond and hence the error is only 0.01 units. So, this is good, because in 1 milliseconds if I keep on doing it, it would be nice. So, advantages of ultra pulse background correction I want to discuss with you, that is sensitivity loss. I have put 4 tables here. The top one is description and ultra pulse, Smith-Hif-J and Zeeman background correction. These three, all these three we have discussed earlier, and now I am trying to compare all the three. So, sensitivity loss in ultra pulse background, there is absolutely no sensitivity loss, whereas in Smith-Hif-J correction up to 6 times the sensitivity loss can occur. That means, the detection limit can increase by about 6 times if you use Smith-Hif-J, and if you do it with Zeeman, up to 3 times the sensitivity loss can occur. So, in flame and vapor generation, if you use ultra pulse correction, then there could be interference, and then there could be interference in Smith-Hif-J, but in Zeeman it has no effect. So, calibration linearity would be normal in ultra pulse, slightly reduced in Smith-Hif-J and normal in Zeeman effect background correction. So, the dynamic range is also very normal in this case, but in Smith-Hif-J and Zeeman it is curved. That means, the linearity could get affected to some extent in both these systems. So, it does not mean that in atomic absorption only linearity is required, but so long as you are able to give reproducible results, the curved the range also can be used. So, the number of readings when you take per second is about 200 in ultra pulse background correction, that is with deuterium lamp. Every 200 readings if you take per second, that is approximately about 3 readings per milliseconds and per second, and in Smith-Hif-J it is about 10 readings per second, and in Zeeman it is approximately 50 times. So, the error would be much less in Zeeman than in Smith-Hif-J as well as ultra pulse. So, background measurement delay is 1 milliseconds here, here it is 4.5, here it is 10 milliseconds. So, 90% of the atomic absorption instruments being sold today come with deuterium background correction. So, it is important for us to know what are the different types of what are the advantages of deuterium background correction as well as disadvantages. Advantages I had discussed with you earlier in the previous one, that is sensitivity loss is nil, then vapor generation it is good, and calibration is linear normal, and number of samples are 200, background measurement delay is only 1 millisecond, but the associated advantages are incorrect results in presence of structured background. That means, if the molecular absorption has got a structure, that means specific absorbance at specific wavelengths, then the background correction does not work. So, spectral interference it is impossible to correct using deuterium lamp, because it is a broadband absorption. Then different geometrical and optical paths are required for deuterium background. That is another disadvantage. That means, it makes the optics more complicated than the Zeeman etc. And then there is sensitivity loss or intensity loss of the light, that is it reflects on the calibration range. In spite of that, hydrogen deuterium background correction is most widely employed. Only since last 10 years we have other types of atomic absorption background correction, that is Smith-Hif-J as well as this Zeeman effect background correction. So, this Smith FJ we have discussed earlier, that is brief pulse of very high current is passed through the lamp causing self reversal, and we can subtract when self reversal occurs, there is only background correction, and by subtracting one from the other true absorbance is obtained. I would like to show you this slide of what we have discussed for a brief this thing, because we have discussed this already. I will not dwell more on this. And then advantages of this method are, it can be used in the UV visible range, accurate correction for structured background. This was not there in the deuterium background correction. So, a single light source is required. You do not need the deuterium lamp for this, only the hollow cathode lamp. So, correction of spectral interference, it is possible, and calibration curve does not bend. That means, you will get a fairly linear calibration curve. So, another way of doing this is to do the modulation. The signal received by the detector consists of the resonance radiation from the hollow cathode lamp as well as the resonance emission line from the atomic source, and for atomic absorption measurements only resonance radiation originating from the source lamp is to be measured. To achieve this selectivity, the lamp output is therefore coded by modulation, and the post detector amplifier is tuned to the same modulation frequency. This is called as lock-in. This prevents the DC emission signal from the flame being measured. From the flame we always get DC signal. So, the modulation can be done only for the non-continuous radiation. So, either by square wave technique AC supply current or by interposing a synchronous chopper in the light beam. So, what I wanted to tell you regarding this modulation is that whenever you are doing this atomic absorption by hydride generation, by deuterium background correction, modulation is required, whereas for self reversal, Smith FJ and Zeeman effect background correction, modulation is not required. So, I have just tried to put in exactly my thoughts about the background correction for your benefit, so that you should be aware of the different types of interferences that can occur, which we have discussed so far. That we have discussed the instrumentation, we have discussed the mechanism, we have discussed the interference, and we are fairly well aware that most of the atomic absorption systems can be used to analyze the elements by using flame atomic absorption spectrometry. Now, this was flame atomic absorption spectrometry was the first AAS system that was commercialized since 1955, and the flame atomic absorption is not really useful for all the elements. There are some elements which are not very ideal, which are not determined ideally by flame atomic absorption. For example, some of them could be non-metals like carbon and then sulfur and the chloride, bromide, iodide, anions, phosphates. These are not determined by atomic absorption, only the metallic elements. Even among the metallic elements, not all the metals can be determined by atomic absorption. because for sodium, potassium, etc., they are all alkali and alkaline earth metals, fairly decent flame emission method itself can be used for ppm level of determination using atomic absorption, flame atomic emission. Now, below 300 nanometers, there are certain elements which will provide which are not easily determined by atomic absorption, whose resonance line is less than 300 nanometers. Some of these include arsenic and selenium. I mentioned these things briefly in my earlier discussion today only, and some of these elements which are not conducive for atomic absorption by flame, they can be determined by slight modifications, and the elements who have got the capability to form hydrides are very easily determined by using an accessory called as hydride generation accessory using flame atomic absorption spectrometry. So, arsenic, selenium, titanium, germanium, antimony, lead, etc., they all form hydrides. So, all these elements can be determined in parts per billion level using an accessory called as hydride generation accessory and normal flame atomic absorption. So, we have three accessories like that. One is for the determination of hydride forming elements, another is cold vapor mercury determination, that is a separate accessory available with atomic absorption spectrometers. And in many of the atomic absorption spectrometers, you can have a just at the flick of a button, you can flick of a switch, you can measure the atomic absorption as well as atomic emission. You can choose what you want to measure. So, atomic emission you can do for sodium, potassium, lithium, etc., some of the alkali and alkaline earth metals. So, this also is available as an accessory or at the switch of a button. So, we will be discussing these hydride generation and cold vapor mercury and flame atomic emission in the next classes. Now, I want to continue, give you a small introduction for the hydride generation AAS. So, in hydride generation AAS, atomic absorption technique, the elements what we will be discussing are arsenic, antimony, bismuth, selenium, tellurium, lead, mercury and a number of other elements of the periodic table belonging to group 4, 5 and 6. These elements are known to form hydrides with, they are known to react with hydrogen to form hydrides which are covalent compounds and they are volatile. If you take these metals solutions and bring them in intimate contact with nascent hydrogen, they form hydrides. There are some tests known as Marsh test and Goodside test for the determination of hydride of arsenic, and they have been employed for the detection of arsenic since more than 100 years. It is nothing new about it, but what is new is the utilization of the hydride generation property of the atomic absorption as an accessory to the flame AAS. The property of volatilization as a gaseous hydride can be utilized to advantage for the separation as well as enrichment of the analyte element corresponding to these elements: arsenic, antimony, bismuth, selenium, tellurium, lead and mercury. It also accomplishes reduction, and even complete elimination of interferences can be obtained in using this accessory. So, in the early 50s, a number of analytical methods based on the colorimetry were introduced for the determination of arsenic and other hydride. So, the basic work was done much earlier for the determination of analyte elements. So, the simplest way of forming a hydride is to take an acid solution using zinc powder, and the gaseous reaction products are to be conducted into solutions containing ammonium, molybdate or hydrogen sulphate, which formed characteristic color complexes with the hydride. This was the spectrophotometric basis. Some of these techniques are still in use even today, but in 1969 first attempt to apply hydride generation technique to AS was used, and he generated arsenic hydride and collected it in liquid hydrogen. Subsequently, he just warmed the trap and conducted the arsine with a stream of nitrogen into an argon flame to measure atomic absorption. Subsequently, several papers were published in the following years describing modifications and optimization. However, the technique has found wide acceptance only after the reliable accessories were introduced into the market. Today, for the determination of arsenic, antimony, selenium, tellurium, bismuth, germanium and lead, hydride generation is the technique for the for parts per million or parts per billion level. We will continue our discussion in the next class.